So do you remember at the beginning of this course we asked what is the difference between probability and statistics? Probability allows us to infer something about what we would expect to observe in a population. In session 2, we introduced probability distributions, which allowed us to make probability statements about values of a random variable. For this, we learned about the relevant parameters for the distribution. And for example, in session 3, we studied at length our normal distribution with the two parameters, the mean and the standard deviation. And also in session 3, we introduced the concept of sampling. We have a population with many, many elements. We take a sample, just a few elements from our population, and we can calculate the sample average, x bar, and the sample standard deviation, s. And then we also use the central limit theorem, where, looking at the distribution of x bar, we knew that if we knew the population parameters, mu and sigma, from our distribution of our random variable x, then we could also know the population parameters of our sample average. So the only problem here was that in order to do this, we needed to know the parameters of our population, and this is normally not the case. So, looking back at the slide, do you remember we said when you don't know the model, we can then use statistics to infer what the model of our population is. And this is the meaning of inferential statistics. These are the techniques that allow us to use a sample from a population and to use the sample to make generalizations about the population. The sample, of course, must accurately reflect the population, and we're aware that a sample is subject to sampling error. So we do not expect our sample to perfectly represent the population. The methods of inferential statistics are the estimation of parameters and testing of statistical hypotheses. And the next part of our statistics lectures will be concerned with these two inferential techniques. But for this, and to finish the lecture today, we need to start with the concept of point estimation. So if we assume that the population we are dealing with is normally distributed, we just need to know the two parameters, mu and sigma of the population. Now the problem is the exact values, as we just said, are very difficult to know or are never known. And we need to estimate them using sample statistics from samples. A statistic that is chosen to estimate a parameter is called an estimator for that parameter. Now, a few statistics may be available as candidates for being chosen as our estimator. For example, the sample average or the median can be used as an estimator for mu, the mean of a normal population. And our sample standard deviation, S, so the sample range, we just mentioned those two, can be used as the estimator for sigma, the standard deviation of the normal population. But certain criteria are used to select a good estimator from our available candidates. Being unbiased is one of the very desirable aspects of properties of an estimator. And an estimator is said to be unbiased if its expected value, which means the average value over many samples, equals the parameter being estimated. And here we're using the notation E with brackets to denote the expected value or the long-run average value of a random variable. And it can be shown for normal populations that the expected value of x bar is indeed the mu, or the mean of our population, and also the expected value of the median is the expected value of our normal population. And the expected value of s squared is the variance of our normal population. So what this means is that x bar, or the sample median, are unbiased estimators for our population parameter mu, and the variance s squared is the unbiased estimator for the variance. Now, if several unbiased estimators are among the candidates, so we just saw x bar and median, then the one with the least amounts of variability is our preferred candidate. And such an estimator is called the minimum variance unbiased estimator, or MVUB, minimum variance unbiased estimator. And for normal populations, the MVUBs for the variance are x bar and s squared, as we've been talking about all along. So we can use these as good estimates for our mean and variance of the normal population, and use these to make inferences about, use these two statistics to make inferences about the mean and the standard deviation, or the variance of our normal population. So finally, we talk about the point estimates. A point estimate is the value of an estimator observed in a single sample. The point estimate, of course, is one observation of a random variable. And the problem is that if we're just looking at one sample from our population, especially if we have small size samples, it's not such a useful piece of information. What we need to do in this case is use what we call interval estimation, where we create an interval using our point estimate such that the probability of the parameter of interest lies in that interval and is of a certain value, which we title 1 minus alpha. And this is called a 1 minus alpha % confidence interval for the parameter. This is one of the two techniques for inferential statistics. We take from a single sample our point estimate, and we conduct an interval estimation then to help us draw conclusions about that statistics to gain information about our population parameter.